Lesson 5E, Free Falling Bodies. The most familiar example of motion with nearly constant acceleration is a free-falling body under the influence of the Earth's gravitational attraction. Such motion has held the attention of philosophers and scientists in ancient times. In fact, in the 4th century BC, Aristotle thought erroneously that heavy bodies fall faster than light bodies in proportion to their weight. 19 centuries later, Galileo argued that a body should fall with a downward acceleration that is constant and independent of its weight. Experiment shows that if effects of air can be neglected, Galileo is right. All bodies at a particular location fall with the same downward acceleration, regardless of size and weight. If, in addition, the distance of the fall is small compared with the radius of the Earth, and if we ignore small effects due to the Earth's rotation, the acceleration is constant. The idealized motion that results under these assumptions is the so-called free fall, although it includes rising as well as falling motion. Figure E.1 shows a falling ball made with a stroboscopic light source that produces a series of short, intense flashes. As each flash occurs, an image of the ball at that instant is recorded on the photograph. There are equal time intervals between flashes, so the average velocity of the ball between successive flashes is proportional to the distance between the corresponding images. Notice that there is an increasing distance between images. This means that the velocity is continuously changing, or that is, the ball is accelerating downward. Careful measurements showed that the velocity change is the same in each time interval, so the acceleration of the ball is none other than constant. The constant acceleration of a freely falling body is called the acceleration due to gravity, and we denote its magnitude with the letter g. That is equivalent to the value of 9.8 meters per second squared near the Earth's surface. We will frequently use the approximate value of g at or near the surface of the Earth. The exact value varies with location, so we will often give the value of g at the Earth's surface to only two significant figures. Now, because g is the magnitude of a vector quantity, it is always a positive number, despite the fact that the direction of the acceleration due to gravity is always directed downward. Here's a sample problem to exercise our problem-solving skills. A 1 peso coin is dropped from the highest floor of one of the country's top rising towers in Mandaluyong City. It starts from rest and falls freely. Compute its position and velocity after 1 second, 2 seconds, and 3 seconds. To go about the problem, we first identify. Falling freely means that it has a constant acceleration due to gravity. So, we can use the constant acceleration equation we learned recently to determine our target values. We then draw or sketch our interpretation of the presented motion in the problem. Now, the motion is vertical, so we can use a vertical coordinate axis and call the coordinate y instead of x. Then, we replace all the x's in the equation by y's. We take the origin O at the starting point and the upward direction as positive. The initial coordinate y sub 0 and the initial y velocity are both 0. The y acceleration is downward in the negative direction, so a sub y is just the negative of g, and that is negative 9.8 meters per second squared. Remember that, by definition, g itself is always positive. Our target values are the values of y and v along the y at the three given times. To find this, we use the kinematical equations that we've learned previously. We recall that the kinematical equations are given as follows. To find our target variables, we use equation 1 and 3, replacing x with y. At the time t after the coin is dropped, its position and y velocity is given by these equations respectively. Now, we shall use this as our base equations for the next step. Using our base equations, we find that at t equals 1.0, the coin is 4.9 meters below the origin and has a downward velocity with magnitude of 9.8 meters per second. Consequently, the position and y velocity at 2.0 seconds and 3.0 seconds are found in the same way. Upon evaluation, we can see that all of our answers are negative because we chose that the positive y-axis points upward. If we have chosen the positive y-axis to point downward, then in this case, our acceleration g, including all of our answers, should have been positive. Either choice of axis is fine. Just make sure you state your choice explicitly in your solution and confirm that the acceleration has the correct sign. Here's a practice problem you might be interested with. You may do this to exercise your problem-solving skills at any convenient time. Contents of this presentation is taken from the following references.